Video Lecture 6.2, Plate Tectonics. Although the professional geologists in the house might cringe at this analogy, we have on our right-hand side our Mother Earth that's very much like, on the left-hand side, the hard-boiled egg. If you know what a hard-boiled egg feels like, it's got that very thin yet brittle outer shell with the plastic, almost gooey-like inside. Very similar to what we would find on the right-hand side with our Mother. Here we have a lava lamp. A lava lamp is another analogy we can use to understand what Earth is like in the inside. What a lava lamp is pretty much probably something that sits around in dorm rooms at IU down in Bloomington, where college kids probably stare at this and for 5 hours, while IUPUI students are off doing work and doing good things. Anyway, so if we think about this, we can relate this to our Earth, where we have a core, which is where the warmest temperatures are, and from there we've got this molten magma material that wants to escape, and so it wants to go through the mantle and go through and eventually get to the crust. And so another way to conceptualize this, if you stared at a lava lamp, you would see this. You'd see this gooey stuff rising to the top. Very similar to our Earth. First off, you need to explain what we're looking at here. This is a cross-section of Earth. So essentially here we have Earth, and we just slice right down the middle of it. Now we're looking at it from the side view after cutting and slicing it right in half. So there in the center we've got the inner core, which is solid metallic iron and nickel, which is why it's colored that color there of silver. Then we have that outer core, which is essentially molten material, extremely hot temperatures. Then from there we've got the lower mantle, then much of the mantle, then finally we have this kind of greenish line right before the crust, and that's the upper mantle. It's greenish because it has the mineral olivine, which is green in color. And so that outer crust, we once again can relate that to the thin, brittle shell that we'd find on a hard-boiled egg. And so the lithosphere is the analogy of that thin, brittle outer shell of a hard-boiled egg. One of the things is the lithosphere is also referred to as the crust and the upper mantle, which we can see there in that yellow box. Further, the continental crust is thicker than the oceanic crust. Not important right now, but we'll come back to that idea here in a minute. And once again, the lithosphere is that thin, rigid, brittle outer shell that, as we say at the bottom, floats on a slowly moving asthenosphere. And the asthenosphere is that plasticky, gooier part of a hard-boiled egg. And here we're going to find a weaker, yet hotter part of the mantle, where we have a lot of that molten material. So think of that when you think of a volcano spewing all of that lava. That molten material was what we would find here in the asthenosphere, of course, at much warmer temperatures. We go back over to the cross-section view. Those arrows indicate that molten material, it wants to escape. That hot temperatures, we know this warm air rises, and so in this case it expands and wants to go out in all different directions. And so one of the things we're going to find is that the warmest temperatures are going to be found closer to the core. The cooler temperatures are going to be found more towards the outer part of this cross-section here. So another way we can visualize our lithosphere and our asthenosphere is here on our lava lamp. This here is an image that we'll see time and time again throughout video lecture 6, so let's understand what we're looking at. In the yellow box on the left-hand side, we see the location of the lithosphere there in gray, and the asthenosphere in pinkish, reddish, salmon-colored below it. Further, we can see the oceanic crust is going to be thinner than the continental crust over on the right-hand side. Now we return to our good friend, the hard-boiled egg. And so we know the inside of this egg, we have that warm, hot inner part that heat wants to escape. And it wants to escape, it wants to expand outward. Of course, as it expands outward, what's going to happen? We're going to get cracks to form. One of the things we can relate this is to individual little bits and pieces, or we'll call them plates, let's say. Along this red line that we see right through the middle, let's imagine that along this red line, you get separation occurring. So all along this red line, the plates are getting essentially further apart from each other on opposite sides of the red line. So what's that going to do? It's going to create actually collisions on the other sides. And so the idea is red lines, along this red line we got separation. What's going to happen is on the other side of these individual plates, they're then going to collide. And so we're going to see along those blue lines collision. Very fundamental idea to understanding plate tectonics. Let's talk about a German dude named Wegener and his theory. This guy is kind kind of bad luck in the sense that his idea he came up with before World War II, but it really didn't gain traction, really didn't gain momentum until after World War II in the 50s and 60s and 70s, and at that point he was pretty old and already dead. One of the things is this theory is something that's kind of new in the sense that you're part of the first few generations that are actually learning about this whole idea of plate tectonics. It's a rather simple idea. First off, his theory was that 225 million years ago or so, the land masses that we see today, North America, South America, Africa, Europe, those continents at one time were all one massive supercontinent, and that supercontinent was called Pangaea. And it has different terms, or different pronunciations, but who cares? One of the things is 225 million years ago, one massive continent in which over time the continents have separated. However, we're about 275 million years away from all the continents coming back together on the other side of the world. Further, this whole idea is based on the concept of continental drift. And essentially what's happened over the last 225 million years is all the continents have drifted away from Africa. Africa has pretty much remained in the same spot. It's moved a little bit, but all the continents have pretty much broken away from the continent of Africa. Continent, not a country. Further, the idea here is these continents are resting on top of what we call tectonic plates. And we can go back to the previous example of the hard-boiled egg to think about those individual bits and pieces I showed beforehand are what we call tectonic plates, or an analogy of tectonic plates. And that's where we have fragmentation or cracks in our lithosphere. Further, the slabs of crust that the continents rest on, they essentially move over the ionosphere. And so these tectonic plates, they move. And so this idea is compounded in the fact that they collide with other plates, as I showed on that blue line in the previous slide. And these collisions then, of course, can produce earthquakes, volcanoes, and mountains, and are essentially the land creators I talked about at the beginning of video lecture 6.1. And of course, where does this whole tecton word come from? It's Greek for builder, kind of idea here. We're building, creating land. One very simple, basic idea to help prove Wegener's theory is if you look at the continents. Here we have North America on the left-hand, top left. We've got Africa there in the bottom right. We've got on the bottom left, South America. And if you look, they kind of, if you put them back together, they all fit together, almost like they're perfect jigsaw puzzle pieces. And that's one simple way to showcase and explain, improve, and justify our good friend Wegener's theory. Although it might be hard to fathom, the Appalachian Mountains that we showcased in a previous map quiz, and the Atlas Mountains, another previous map quiz location, they at one time were right next to each other. So over time, Africa, the northwestern part of Africa, and the southeastern part of the United States, the eastern part of the United States, have over time separated. In fact, the same event, there's an event that created the Appalachian Mountains and in the Atlas Mountains, actually created the same mountains at the same time that we would find up in the British Isles, up in parts of Scandinavia and Greenland, showcasing the idea of, once again, plate tectonics. They're moving. Even further evidence of Wegener's theory is the fact that dinosaur fossil remains have been found just in certain areas of these continents that are today separated by large water bodies and oceans. So, of course, these suckers, they couldn't fly in many respects, or they couldn't swim across the entire ocean. And so why would their fossil remains be found in these certain areas? Well, at the time, the continents were all together, and there were no oceans separating them.